Okay, here we go. All right, welcome to Special Relativity 3. You've missed 2 already if you're just starting on this one, so please go back. This is going to be some of the even stranger stuff than the paradoxes we dealt with in Special Relativity 2. These are some of the hardest ones that sometimes professional physicists have argued about for decades, but they're very simple and they're really, really cool. So I'm Robert Nemiroff. This is Michigan Tech. This is Physics X and Extraordinary Concepts in Physics, where I will go through what I think are some of the coolest concepts in physics. This is an actual course being taught at Michigan Tech with no textbook required. Okay, so let's get to some of the, this will start easy, I guess. Here's the twirling pole paradox. So let's say you hold a very simple, very long pole. You hold one end firmly, but you're bored just holding the pole. That's not fun enough. So now what you're going to do is you're going to twirl the pole around. You're standing there with your pole. Here's your long pole. And now you're going to twirl it. You're going to move it like this. Now, let's say this is a really long pole, light years long. Can the far end, this end move faster than the speed of light? If it's really long, wouldn't that happen? We're just used to short meter sticks, so it doesn't happen inside our lab. But let's say it was a really, really long pole. It was a light year long, and you swing it around in a second from in front of you to behind you. Doesn't the end of that pole have to go faster than the speed of light? But then again, isn't that a real thing? If you had a note on the pole, couldn't you then be communicating faster than the speed of light? Think about it. Strange. So I have 3 answers here, no, yes, and where's the barn? I thought this paradox had a barn. And we'll jump into the answer. Once you've unpaused me, I'll freeze to confuse you. No. Every physical object must travel less than c. You cannot swing your pole such that the end moves that fast. Why not? This is a little bit different than the faster than light stuff we dealt with the paradoxes last time. Well, the pole end is real, and nothing real which can carry information can move faster than speed. Here's what happens. When you move the pole, so here's the pole here, and you're here. When you start to move the pole, the information that the pole is moving can only move up the pole at a fastest speed of c. So the information can only move this up the pole at c. So that this pole should be over here as it's being swung like this hasn't yet reached this part of the pole. It doesn't know. This part of the pole is completely clueless. So this gets into what you would think would be not relevant to special relativity strength of material arguments. If this is a completely rigid pole that always must be straight, it can't exist, because the information that it's bending has to move up the pole. Therefore, anything completely rigid is a violation of special relativity. What happens is a perfectly rigid pole, let me clear it, a perfectly rigid pole would break. A very elastic pole, you would find, would start spiraling around. And at no point would any part of that pole move faster than the speed of light. It's just a simple pole. You just make it long and strange stuff happens. That's our strange universe. All right. Forget these poles. Let's deal with the scissors. Everybody's dealt with scissors. How could a scissors be strange? Well, let's think about it. Can the vertex point of a scissors move faster than the speed of light? So here you have a scissors like this. Let's say here's the handles. Here's the vertex point, and you decide to close the scissors. Does this vertex point here, it's going to move like that. Can that move faster than the speed of light? Well, is that a real point? Well, these scissors, they're made of, say, metal. So is the vertex made of metal? So is this just like the blinking paradox, or maybe it can because the vertex isn't a real point, or is the scissors real enough so that point can't move? And maybe the most important thing is to walk, not run when carrying scissors. Weren't we told that? So pause this if you like to contemplate, and I love to contemplate. I've contemplated these for long periods of time. And here's the answer. It's actually really complicated. Even the scissors at your desk is complicated. Now, for a standard scissors starting from rest, the information that the scissors is closing is sort of like the twirling pole paradox. The information that the scissors is closing can only move down the blade. let's say one of the blades is moving at slower than the speed of light. Therefore, if you start with the scissors at rest, the vertex cannot move faster than c. It's constrained because the information the scissors is closing is constrained. However, once the blade is moving, that's off. So let's say you had two lines here that were roughly parallel, one here and one like this, and they cross here. So this is the vertex. So this one now is completely moving. The whole length of it is moving at constant speed down. But they're nearly parallel. Therefore, this vertex point can shift across at arbitrarily high speed once the whole thing is moving. So once one of the blades is moving completely along its length, the vertex can zip. And the vertex can shoot across at faster than the speed of light. So you can have a light-year-long scissors just shown by the two things moving, by one blade moving down past the other, and that whole scissors can close in a second, even if it's a light-year long, and then the vertex is shot across at much faster than the speed of light. This assumes completely straight scissors. If you want to get really strange, start considering curved blades, and then you actually get into a bit of catastrophe theory where you can have points, some points created that are moving, dual points created that move away from each other, but that gets really strange. So let's jump past that a little bit and again say that no matter what happens, even if you have your scissors and you have a vertex, if you put something at the vertex, you can't push it at faster than c. So this thing, which is a real object, can't be shot out at faster than c. You might be able to use this as an acceleration mechanism in some way, but real objects can't go that fast. So if you have something, it's not going faster. And you also can't use it to communicate. You might be able to close your scissors, but you can't use that to communicate something to people. If you're at the handle of the scissors, you can't communicate to the pointy tip of the scissors faster than c. And that's the solution to that paradox. Okay, so it's really fun to consider different points of view, too. So let's say that you were in the case of the scissors where the whole thing is moving, so the vertex is shooting down the scissors at faster than c. If you were to live at the pointy tip of the scissors, what would you see? You would see the vertex moving toward you at faster than c, but wait a minute. If it's moving faster than c, it's going to get to you before anything else. So actually what you're going to see is the vertex will just suddenly shoot to you and then start moving away from you. So when things appear to move faster than the speed of light, they can actually appear to move in the opposite direction. At the handle of the scissors, it'll be a little bit different. The vertex will appear to move toward the pointy tip, but it will appear to move faster than the speed of light, so far as I can tell. Stranger yet is the midpoint of the scissors that's moving when the vertex is moving faster than c. At that point, you're actually going to see the scissor close in two directions. The vertex point will jump toward you at faster than c, but then start moving away from you in that direction. But in the other direction, it's still going to move away from you. So you're going to think you're at a cross point where the two vertexes are moving out from you. So if you make scissors really large and you close them really fast, very strange effects appear to occur. But no communication faster than c is happening. Okay, another one, I guess I won't go into too much detail, is the illumination front paradox. So here you have a board, and here you have a flashlight here that's emitting photons. And this flashlight photons is giving what's called a wave front, where all these photons are coming toward you right there, and this wave front is going to hit the board. And if you range it right, it'll hit the top of the board and the bottom of the board at the same time. And the board will just be instantly illuminated. And that's fine. Now, though, let's assume that this wavefront is, or this board, slightly tilt this board. So slightly tilt it, so now it's like this. Now it's going to hit at the bottom. The wavefront of photons is going to hit the bottom slightly before it's going to hit at the top. And what's going to happen is that wavefront is going to illuminate the board from the bottom to the top, and that wavefront's going to climb the board faster than the speed of light, but no information is being sent that way. So this is an unusual thing. However, it's the most common thing that you will ever see, because whenever you turn on lights in a room, there are things like that happening. Not only that, there's if the lights are coherent enough, there are interference effects where the interference patterns are zipping across wavefronts faster than the speed of light. And wave fronts are moving all over this room, but they're happening so fast that you can't see them because your eye integrates for 1/10 of a second. So you're missing some really cool special relativistic effects. But there's nothing you can do about it. The ladder paradox, this is a famous one. Okay, I used to hear about it as the pole in the barn paradox. And so I worried about this a lot when I was an undergraduate. So you hold a really long ladder and you run toward a short garage. Is it true with Lorentz contraction that if you run fast enough, you can trap the ladder in the garage or the pole in the barn? And so worried about that for a long time. And the answer is, I didn't have a 3 you can guess at. The answer is, strangely enough, yes. Yes, you can trap that ladder in the barn. Here's how it works. The front of the ladder is going to hit the back of the barn. And the information that happened is going to move up the ladder, but not instantly fast. It can only move up the ladder at the speed of light. So by the time it gets to the front of the ladder, or the other side of the ladder, that might already be inside the barn or the garage. And you just close the door. So if your job is to guard the door, someone runs by holding a really long ladder, they're going to hit the far end, and the information that it's collapsing is going to move up the ladder, but it might not get there before you have a chance to close the door. So you can slam that door shut, and you've trapped that long ladder in that short barn, in that short garage. And then you get to see what happens, which is stronger, the ladder or the door. Although the ladder might have already crumbled because if it's too rigid. So that's one of my favorite ones. Probably the most popular one is the twin paradox. The twin paradox has one person stay home and the other one zip away on a spaceship really, really fast. And then they turn around and they come back. And the question is that if you looked at that from both sides, would each twin think the other one is older? Or does each twin think the other one is the same? Which one? Does one twin get to be older? So this is a classic paradox. Lots of people have debated this for a long time. And the answer is the twin who rocketed away will come back older. It's the answer to this experiment. So you can use this. I'm sorry, actually it's phrased wrong. When you get back, you will find that people have aged a lot more. So actually I should actually edit this. When you come back, when one twin comes back, those people have aged a lot more. This is the basis of some movies with monkeys in them, in fact. Apes in them, sorry. So this is a way you can travel into the future. The difference is that the twin who went away, is different from the twin who came back, because the twin who went away actually experienced acceleration before they could come back, and that changes it so they can't just use a straight Lorentz contraction on time dilation. They can't do it. So there is a difference. So how can you tell if you're moving? If you have a coffee cup and you're drinking your coffee, and you can drink your coffee fine the whole time and it never spills, you're good. If suddenly it sloshes around, watch out. You're not in an inertial frame anymore. You can't use those same simple transformations. Okay, with that, I'm going to have to conclude and do the next part of this lecture next time. And remember, please keep Schrodinger away from your cat.